So the materials that do have a lot of technological importance are liquid crystalline materials. And as I mentioned, they have long-range orientational order, but not the positional order. And just to tell you a little bit about the history again, how these materials were discovered. So it actually happened relatively early on in 19th century. What was discovered is that if you take a particular type of a material called cholesterol ester, and if you measure a heat flow as a function of temperature using a method called DSC. Are you familiar with this technique? You've used it in 314. What is DSC? Differential scanning calorimetry. That's right. So what you're measuring is you're basically measuring what is the heat flow that is required to keep the material at a certain temperature, right? So if you start from a relatively low temperature, this material will be solid. And at a certain temperature, again, for this particular material, what happens, it happens to be at 145 degrees. The material goes through a phase change, and you can see this from this peak in the DSC scan. And it turns out that this material becomes haze, and it flows. And if you continue, you would have yet another peak, and the material will become transparent and liquid. So if this was just a standard type of a material, let's say crystalline material, it would have only one particular peak because it would transition from solid to liquid. But certain types of materials can exist in the liquid crystalline phase. What this tells you is that the material itself can have a solid crystalline form. It will transition to a new state of matter called liquid crystalline state. And when you increase the temperature, it will become completely liquid. Right? So these are just three different forms of the same type of material that can exist at different temperature ranges. Okay, so what is the difference, or what is really happening is that in the solid phase, again, these molecules will have the same orientation, and they will be precisely positioned in space. So this would be the crystalline form. When you increase the temperature, this positional order would be destroyed, but the molecules, because they're highly anisotropic, will still have this orientational order. And when you increase the temperature and you come to this temperature range, which again for this particular material happens around 170 degrees, you will eventually have the material that is completely liquid-like, right? So even this orientational order is lost. Okay, so liquid crystalline materials, as I already mentioned, have highly anisotropic shapes of the molecules that constitute them. So these are either very long molecules, they can have disc-like shapes, or some of them they're so-called banana liquid crystalline materials. But what they all have in common is the fact that they're highly anisotropic. What that means is that one dimension is significantly larger than other dimensions of that particular molecule. So in the case when you have a material or the molecule where the length of the molecule is significantly larger than the diameter, this is so-called rod-like or calamitic. So when you hear a word calamitic liquid crystalline material, it simply means that the molecules that constitute that material are rod-like. So then if they have disc-like shape, so what that means is that the diameter is significantly larger than the height of the molecule. So this is disc-like. So these will be called discotic. Again, I already mentioned there are other types but these are the most common. So the calamitic and discotic liquid crystalline materials are the most common ones. Okay, so to summarize about what we learned about general order in crystalline, liquid crystalline, etc. Materials, what we know is that for solid crystalline materials we have both positional and orientational order. For plastic crystals we do have the positional, but we lack the orientational order. For the liquid crystals, it's the opposite case, so the orientational order is preserved. And for isotropic liquids, we don't have either, right? But again, the message is that a given material or a given molecule can form one of these forms. So again, the plastic crystals, as I mentioned, are typically spherical, but if you have an isotropic, it can molecule, it can form either a liquid, crystalline, and solid. And one note before also we move ahead is just to say that in the liquid crystalline materials, this orientational order is usually averaged over time. So if you take a snapshot of a liquid crystalline material in time, you will rarely see really perfectly aligned molecules. But on average, over time, you will see a certain orientation. Okay? So this is just one thing to remember as you go forward. So general terms for the calamitic or rod-like type of a crystalline materials, they do have a general form. And this is typically a set of aromatic rings that are connected with different types of connecting units, and they can be functionalized at their ends using different types of terminal functional groups. And again, they can be decorated on sides with different types of side groups, and etc. In general terms, they are these types of aromatic types of structures, and you can arrange them in different ways, and then the side groups themselves will tell you how likely this material will be to exist in the liquid crystalline form, how likely it will form this orientational order, etc. Again, the reactivity of the end groups will tell you also how likely is that this material will eventually form a crystalline material, how it will react with surfaces, interfaces, other materials, etc. So you can actually play with these materials and engineer the liquid crystalline materials with different properties. Okay, so because they have these relatively unique properties, the question is how do we describe their structure, right? So I mentioned the fact that the pair distribution function in principle can be used for these materials, but it's not necessarily the best way to describe them. So in the field of liquid crystalline materials, there is one particular descriptor that is very often used, and it's called a director. So the director will be an average orientation of the molecules in the liquid crystalline phase. So if you look at this liquid crystalline material, you will see that again, on average, the orientation of the molecule is roughly in the same direction, but there is small variation, right? So each molecule has its own direction, which we will call pi. And this is a non-polar vector, so it simply tells you the orientation, but not the direction. So it simply tells you, well, this particular molecule has certain orientation, but we don't necessarily know anything about the direction, right? So we don't actually care about this. So the director itself will be defined as a non-polar vector that describes the average of the orientations, and it will be indicated with this N symbol. And what this symbol simply means is that this is an average of PIs over volume. So if I, for example, have a certain non-polar vector PI, and if this is my director N, this PI will be defined by an angle theta I. So again, the average theta for this particular crystal will be 0, because on average the orientation of the molecules is along the director line, but each molecule will have a small deviation from that angle. So I can also ask you a question: why did I write this as n as a function of r? So why is this director a function of the position, right? R is the position within the material. What does it mean? One thing that can help you is try to look at this optical image of a liquid crystalline material. So this would be an optical image of a liquid crystalline material, and it has different colors in different areas. So why did I write the director is a function of the position? The director itself is locally defined. What that means is that if you have a material, liquid crystalline material, the orientation locally, so if this was my liquid crystalline material, then I can have different domains that are not necessarily strictly separated, they can be continuous, but the orientation of the molecules is locally defined. What that means is that in this area, the molecules will have, for example, horizontal orientation, and therefore the director will be in the horizontal direction. Here they may be slightly different, there will be completely different, etc. And the colors in this image actually represent the change of the director. So when you look at the liquid crystalline material through either polarized light or using optical microscopy, the optical signal will depend on the orientation of the director. Again, what that means is that locally, in this particular area here in blue region, I know that all of the molecules, and there are many of them here, right? They have the same orientation, but when I move here, this orientation will be slightly different. And if you make this liquid crystalline material very small, this is, for example, what is used in liquid crystalline displays, you're trying to make one individual domain, right? So you're trying to make this domain such small that the director is unique to the entire region of the crystal. Okay? Did you have a question?
Is this similar or analogous in any way to magnetic domains? Because you have like domains that have the same orientation and they can be side by side with very different orientations?
So in principle, yes. So in the magnetic domains, you're also talking about the orientations of the spins, and this can be rotated or it can be arranged in different ways. But in a local area, they are all arranged in parallel, and it's a good analogy, right? The physics is completely different, though, but the analogy stands there. Okay. So again, the take-home message is the director is the way to describe liquid crystalline materials, and when you look at then in so-called nematic liquid crystalline materials, which are the liquid crystalline materials that we defined so far, where there is no positional order, but there is long-range order, when you actually look at the director, so the director would be in this direction, and what that simply means is that when you look at the frequency, or the number of the molecules that have a certain orientation, and if this was the angle of the director, so what that means is that if this is my zero orientation and I know that the director is here, I'm sorry, this would be, yes, the director is in this direction, this would be the angle of the director. What that means is that most of the molecules, if I plot their orientation, which is the angle between each molecule and the director, they would be all very closely focused around this particular angle. Right? So there would be a distribution that is relatively narrow, meaning that most of the molecules have exactly the same orientation as the director. On average, there is small distribution, but it's relatively narrow. Okay? So how would this graph look like if I heat this material? So if I increase the temperature, so this is the nematic liquid crystal. It has this particular distribution, and if I increase the temperature, how would this graph change? Yes?
It would get wider until there was no peak anymore?
It would be wider until you have just flat line, right? If this was a liquid, you would simply have a line. What that means is that there is no preferential orientation of the molecules. Okay? So again, this already tells you that the descriptor itself is very useful descriptor for the case of the liquid crystalline materials, but for the liquids themselves, the director doesn't have any meaning. Right? So again, this really emphasizes the fact that for particular types of materials, you have to think about the best and the most appropriate way to describe them. So